Discover Geography, Lesson 3-3, Biogeography. Biogeography involves the study of ecosystems. Here in this picture you see a sample ecosystem, obviously not a real one. An ecosystem consists of the living things in a particular place and their interactions with the non-living environment around them. So in this ecosystem, the trees, the deer, the Tyrannosaurus are all part of the ecosystem, but so are the sunlight, the rocks, and the water. All of these things are interacting with each other. All of these things are shaping each other and therefore make up one ecosystem. Ecosystems are connected by a series of biogeochemical cycles that move energy and materials through the ecosystem. So let's start by looking at the energy cycle. The energy for nearly all ecosystems on Earth begins from the sun. The sun is our major source of energy. Solar energy is absorbed by plants through the process of photosynthesis. They take in that light and heat from the sun and they store it in chemical form. So the energy is converted into chemical energy in the tissues of the plant. So that plant can then be eaten by animals to get that energy. And those animals can be eaten by other animals and other animals, etc., up the chain. Now, solar energy is going to pass through that ecosystem and get used up at each step of the way. So it's not quite a cycle in the sense of looping back around on itself. The energy never goes back to the sun. Instead, it's taken in by the ecosystem and used and dissipated through the ecosystem. Now, any of these organisms living in our ecosystem may die without being fully consumed by any other component of the ecosystem. And so sometimes their bodies will get buried deep underground. So all of the chemical energy that's still in their tissues is now going to be buried. It's going to be taken out of the system. And if those buried remains are compressed underneath the earth for long enough, they can turn into fossil fuels. They become coal, oil, or natural gas, depending on what kind of material we're dealing with and what kind of pressures and temperatures they're subjected to under the ground. So fossil fuels are this reservoir of chemical energy that was absorbed by the plants from the sun millions of years ago. So humans have figured out that we can dig up those fossil fuels and release that energy to power our factories and our cars and other aspects of modern civilization. When we look at how this energy passes through the ecosystem, we're really looking at what's called the food web. The food web is the set of relationships of who eats who. So in this particular example of a food web, this is an aquatic food web, we can start with the phytoplankton. These are microscopic organisms that perform photosynthesis. And we can see they're eaten by the zooplankton, which are microscopic non-photosynthetic creatures. Those are eaten by, for example, fish, which can be eaten by birds, which might be eaten by a fox. So this energy passes through the ecosystem from the phytoplankton up through several steps to every other organism in the food web. At each step of the food web, much of that energy is lost. The general rule of thumb is that of the energy that arrives at a certain stage of the food web, about 90% of it is going to be lost. Only about 10% of it is going to be available to whatever eats the organisms at that stage. So if the phytoplankton have a particular amount of energy that they've stored from the sun, then they get eaten by the zooplankton. The zooplankton will get about a tenth of that energy available to them from eating this phytoplankton. And if the zooplankton are eaten, say, by a salmon, the salmon is going to get 10% of the zooplankton's energy, which is 1% of the original energy that the phytoplankton had. If the puffin eats the salmon, it's going to get 10% of the salmon's energy, which is 0.1% of the original energy from the phytoplankton. So at each step of the food web, you have less energy available. You can support fewer organisms at that level. So we always see lots of plants, fewer herbivores, and even fewer carnivores in any ecosystem. Another important material that an ecosystem needs to survive is carbon. Most of the molecules that make up living things are carbon-based. They have carbon as a key component to them. On our Earth, we have a big reservoir of carbon in the form of carbon dioxide in our atmosphere. That carbon can be taken out of the atmosphere by plants during that process of photosynthesis. The chemical form that plants store the sun's energy in is carbon-based molecules. So plants will absorb that carbon out of the atmosphere, turn it into their own tissues. Animals can then access that carbon by eating the plants or by eating other animals that ate the plants. Animals then breathe that carbon back out into the atmosphere. So animals essentially reverse the process of photosynthesis, release that energy from its chemical form so that they can run around and mate and do all the other things animals need to do. And in the process, as they break down those chemical compounds, they breathe the carbon dioxide back out into the atmosphere. So that's the core of the carbon cycle. Carbon from the atmosphere, absorbed into plants through photosynthesis, who are eaten by animals, who breathe the carbon back out into the atmosphere. Atmosphere to plants to animals, back to atmosphere. However, there are a few side trips that carbon can take. If those animals and or plants die and get buried underground, not only is there energy buried down there, but also the carbon that makes up the molecules that energy is stored in. So our fossil fuels are this giant underground reservoir of carbon as well. Carbon from the atmosphere has been taken out of the system and basically stored away underground over the course of the Earth's history. And so when humans dig up those fossil fuels, we burn them in our factories and our cars, we release that carbon back into the atmosphere. So we take carbon that had been put away, that had been taken out of the system millions of years ago, and we put it back into the atmosphere. When we get to our lesson on climate change, we'll see some of the impacts that that's having on our Earth, that we're returning all of this old carbon to our atmosphere that our ecosystems had not been having to deal with for a very long time. That carbon from the atmosphere can also be absorbed into the oceans. So when there's an excessive amount of carbon dioxide in the atmosphere, some of that's absorbed into the oceans and makes the oceans slightly more acidic. Again, when we get to our climate change lesson, we'll see some of the impacts that that's having on our environment. Another somewhat different biogeochemical cycle is the nitrogen cycle. Nitrogen is another essential element. It's a key component of many of the molecules that living things are made up of. Luckily for us, we have a huge amount of nitrogen in our atmosphere. Unfortunately, that nitrogen cannot be directly used by plants or animals. We cannot just breathe in nitrogen out of the atmosphere and use that. That nitrogen needs to be converted into a suitable form. This is a process known as nitrogen fixing. Nitrogen fixing can happen in two different ways. One way is through the action of lightning. When a lightning strike hits, it fixes some of the nitrogen out of the atmosphere. It converts that nitrogen into a different chemical form and leaves it in the soil. The other way nitrogen can be fixed is by the action of bacteria that live in the roots of certain plants. So clover, for example, is a nitrogen fixing plant because it has bacteria in its roots that take that nitrogen out of the atmosphere and convert it into a different chemical form. Those bacteria give some of that fixed nitrogen to their host plants, but they leave other fixed nitrogen in the soil. Once this nitrogen is fixed in the soil, it can then be absorbed by other plants or by bacteria that return it to the atmosphere. So this nitrogen from the soil can simply return to the atmosphere, or it can be absorbed by the roots of plants that don't have their own symbiotic nitrogen-fixing bacteria. Once the plants have it, animals can eat the plants, and then animals will return that nitrogen to the soil by pooping. So animal excrement, animal feces, contains within it high amounts of nitrogen, and that's why it makes such good fertilizer. It's going back into the soil, it's replenishing that fixed nitrogen that can then be drawn up again by the plants. So with the nitrogen cycle, we see these two kind of loops. We see from the atmosphere to the soil and back again through the action of bacteria, and we see from the soil up through the food web and back to the soil through the action of plants and animals. All of these biogeochemical cycles, the energy cycle, the carbon cycle, the nitrogen cycle, and a variety of other cycles that we're not going to take the time to talk about in this short lesson, connect together both the living organisms, the animals and plants in our ecosystem, and the non-living components of the ecosystem, the soil, the water, and the atmosphere. Now, ecosystems can change their composition over time. This is a process that's known as succession. Succession is the change in the composition of an ecosystem over time. The traditional way to think about succession is that you might start with a bare area, an area where the ecosystem has been destroyed by some sort of catastrophe, or maybe it's a newly emerging piece of land, a new volcanic island is forming, for example. And that land will go through a series of steps until we get to what's called a climax, where we have a fully developed ecosystem. Everything that can grow there is now growing there. The ecosystem has reached its peak state, and that climax is then going to be stable. It's not going to change unless some external force disturbs it, unless people come along and chop it down, or a volcano wipes it out, or some other sort of disaster sets back the system. But then once that disaster is over, succession will ultimately return the climax to its place. That's the older way of thinking of succession. But in fact, that's not quite how it often works in the real world. So let's take the example of the spruce budworm in Canada. So in the ecosystems that the spruce budworm inhabits, scientists had identified a successional cycle that we go from barren ground, where the trees have been wiped out, then spruce trees will grow, and then those spruce trees will eventually be overtaken by fir trees. Spruce trees grow very well where there's a lot of sunlight, so they can grow easily in barren ground. Fir trees are slower to grow, but they can grow in the shade, whereas spruce trees can't. So the fir trees will grow and they will shade out the spruce trees. The spruce trees will die off and will become an entirely fir-dominated forest. So if we leave it at that, we've got a traditional ecological succession from a barren land through one type of ecosystem and eventually into this final climax ecosystem. But what scientists found in Canada was that whenever this fir ecosystem would get going, it would get attacked by this little guy, the spruce budworm, who, despite the name, attacks fir trees, not spruce trees. The spruce budworm would kill the fir trees. And when the fir trees died, we'd then get gaps in the forest. We'd get barren ground again. They would have to be recolonized by spruce trees and then regrow into fir trees. This is a problem because fir trees are a valuable timber species, and so in Canada they wanted to be able to log these forests. They didn't want them to get destroyed by the spruce budworms. And so they started to spray to kill the spruce budworms. They would try to avoid spruce budworm outbreaks by killing them off with pesticides. And at first that seemed to work. They were killing off spruce budworms. They were forestalling outbreaks that would kill large portions of the forest. But what they found was the longer that they sprayed for spruce budworms, the more fir trees would grow. And so therefore, eventually, when they finally did get an outbreak that their pesticides were unable to control, it would be even more devastating. This budworms would be able to just rip through the entire forest because the entire forest was now made out of fir trees. And the longer they tried to postpone the spruce budworms outbreaks, the worse their devastation would be when they finally occurred. This suggests that the fir forest is not a stable climax. It's not just going to stay that way. Because the more fir trees you get, the tastier it is for spruce budworms, and the bigger of a budworm outbreak you're going to get, and that will reset the entire cycle. So there is no stable climax. Instead, there's a constant cycling between barren ground, spruce trees, fir trees, budworm outbreak, back to barren ground. And the ecosystem will keep going through this cycle naturally, unless it's interfered with by people trying to kill off the budworms, postponing the outbreaks, and therefore making the outbreaks worse. This type of phenomenon is common in many different sorts of ecosystems. And so we've developed a general model to explain what happens here? Here you see a forest that's been devastated by a spruce budworm outbreak. Huge numbers of trees have been killed because by putting off the outbreak, that entire forest was able to convert into fir trees that were super tasty to the budworms. Here's our model. It's known as the adaptive cycle. And there are 4 phases to the adaptive cycle. The diagram here is drawn in the shape of a figure 8 rather than a circle for reasons that we're not going to have time to talk about in this lesson. What you need to know is the 4 stages of the adaptive cycle and what happens at each stage to an ecosystem. So we can begin with the R phase, or the growth phase. Here we have a lot of opportunity. We have an ecosystem that has been kind of cleared out by some past event. And so a lot of new things can move in and start to grow during the R, or growth phase. As those things grow, they build up, they make the ecosystem larger, more complex, higher level of biodiversity, higher level of biomass, of the amount of living stuff there, until eventually we get into the K phase, or conservation phase. This K phase is what we used to think of as the climax. So under the older way of thinking, we get to the K phase and we'd stay there unless some external disturbance happened. What we now know is that K phase becomes increasingly fragile. It sets up its own demise. So in the case of the spruce and fir forest, that gets more and more dominated by fir trees and therefore more and more vulnerable to a budworm outbreak. And so eventually, inevitably, there will be some sort of disaster that our ecosystem brings on itself. So it's not an external force coming in and messing things up. The ecosystem brings catastrophe on itself, and that's the omega, or release phase. So this is something like a budworm outbreak, or a wildfire, or a storm that is able to rip down the entire forest because the trees are so old and fragile. The release phase will essentially deconstruct the ecosystem, will tear it all down. And that leads into the alpha phase, or reorganization. This is the phase in which the ecosystem is wide open for something new to grow there. And so once some particular new ecosystem starts to regrow in that place, we move back into the R, or growth phase. So in the adaptive cycle, ecosystems, as they grow and develop, eventually bring destruction on themselves. They create the conditions for some sort of catastrophe that will tear them down, clearing the slate, and allow an ecosystem to regrow in that place. So let's take an example of another ecosystem. Let's talk about conifer forests in the American West. So we might start with an area that's been cleared out by a wildfire. We have new growth will start to grow in that area. A forest will start to grow. Maybe these are lodgepole pines, for example, or they might be Douglas firs. They'll start to grow in this new area, and eventually we'll get a full-fledged forest. The canopy will close, we'll have a huge amount of trees there, and this forest could be hit by a wildfire. If we try to postpone that wildfire, if, say, we send firefighters in to put out any fires that start, we'll continue to get more and more growth. You can see in that picture lots of dead trees laying on the floor of the forest. There's been no fires in a long time. We get more and more material building up. Well, that means more and more fuel for a fire, which means it's easier and easier for a fire that gets started to start to burn out of control so that it can't be put out. So eventually this forest will create conditions where a fire is inevitable. And so we'll have a fire. The fire will burn down the forest. Depending on how much fuel had accumulated by this point, it may completely clear out the forest, or it may just burn off some of the plants in the forest and leave some behind. Once that fire has gone, we now have a situation that's open to something new coming back. The old growth has been cleared away. The old material is torn apart. All of the elements that made up this old growth are now in the form of ash fertilizing the ground. And so we've got a lot of opportunity for a new ecosystem to start growing in this place. And we begin the whole adaptive cycle again.